Alright, so in chapter 4, we're going to be talking about some probability concepts, and at the end some counting concepts. These are going to help us as we move forward in talking about sampling distributions, things associated with sampling from a population, but we kind of need these probability concepts to lay the groundwork. So let's start with an example, and there was one similar to this on your homework. So suppose you have 5 government officials and you want to sample 2 of them. And let's say there's a governor, lieutenant governor, secretary of state, attorney general, and treasurer. And if I want to take 2 of those, well, there's a lot of ways I could do that. All right. So the way I organize them is I start by saying, well, let's fix the governor, and we can match him up with the lieutenant, the secretary, the attorney, or the treasurer. Then we go on to, well, who could we match the lieutenant with? Now, we could match the lieutenant governor with the actual governor, but that was already taken into account here. So lieutenant really can only be matched with the secretary, the attorney, or the treasurer. The secretary could then be matched with the attorney or the treasurer because we already got the secretary here with the lieutenant and there with the governor. And then finally the attorney could be matched with the treasurer. Now, that means that it looks like there's 10 possible unique samples that we could take here. So in this case, since we're taking a random sample, each outcome is actually equally likely. So what would be the likelihood of picking any one of the samples? Well, with 10 possible outcomes, each one should have a 1 in 10 chance of happening. Okay, this proportion 1 in 10, this is an example of a probability. Okay, this is the probability of each sample occurring. So what is a probability? A probability is actually the proportion of times you expect to see an event in the long run. And it's important to note that this is a long run average. So as an example, when we flip a coin, we expect to see half heads, half tails if it's a fair coin. But if you flip a coin 10 times, that doesn't necessarily mean you'll see 5 heads and 5 tails. It's not going to be a perfect 50-50 split. But over time and in the long run, the more times you flip that coin, the closer you're going to get to a half heads, half tails split. Right? So it's a long run proportion. Now, sometimes our events that we're interested in might include multiple outcomes. So, for example, what if I wanted to pick a sample that just includes the Attorney General? Say I don't care about who he's matched with, I just want the Attorney General. So we look at our sample, and there's actually 4 ways that we could get those the Attorney General as sample. So we could see the Attorney General with the governor, the Attorney General with the lieutenant governor, the Attorney General with the secretary, or the Attorney General with the treasurer. So then it would appear that the Attorney General can get picked in 4 out of our 10 samples. So in the long run, that would give them a 4 out of 10 or a 40% chance of being picked. In general, probabilities can be calculated by taking the number of ways an event can occur divided by the number of possible outcomes. In your book, they kind of shorthand this. They write it as an F over N, where F is the frequency, or how often it occurs, and N is the total number of possible outcomes. Let's look at another example. So suppose that you're going to roll a 6-sided die, right? So just your standard die that has the numbers 1 through 6 on it. What's the probability that it lands on an even number? Well, the total number of possible outcomes, there's 6 of them, right? You could get a 1, 2, 3, 4, 5, 6. And how many of them are even? Well, you look at the even outcomes here. That's going to be either 2 or 4 or 6. So the probability of getting the even number then would be, well, 3 ways to do it out of 6 possible. So that reduces to a 1/2 chance, or 50%. All right? So that's basic probability counting. Some of the notation we use, that we just try to shorthand this so we don't have to write as much. We typically denote events with capital letters. So the experiment of rolling the 6-sided die, we could define, say, the event A to be that the die lands on an even number. Okay, so then I'm going to use that capital A in place of writing out die lands on an even number over and over. The probability notation we use to shorthand it too, so if we were interested in calculating, say, the probability that it lands on an even number, well, we use this capital P, and then the parentheses. And what's in the parentheses is what we're trying to calculate the probability of. So P of the die lands on an even number, that's read as the probability that the die lands on an even number. And if we've already defined this event as A, then we could even shorthand that to P of A. So this P of A is the probability of event A occurring. And what is event A? Well, event A was that the die lands on an even number. Okay, so this is a notation we're going to use from now on for probabilities and events. So there's a few properties then of probabilities. The first is that a probability always has to be between 0 and 1. That means you can't have something that happens less than 0% of the time, and you can't have something that happens more than 100% of the time. If the probability is 0, that means it never happens. If the probability is 1, it means it always happens. Alright, so these are basic properties or rules for probabilities. So if you're working on a problem and you keep getting probabilities that are not between 0 and 1, there's a good chance that you're making a calculation error. So you're going to want to check your work. A couple terms that we've been tossing around here that I'll kind of formally outline. Outcomes, those are possible realizations of a random experiment. So that's like when I flip a coin, one outcome could be heads, one outcome could be tails. The sample space is the collection of all the possible outcomes, and we usually denote that with a capital S. And then events are collections of outcomes that we're actually interested in seeing happen. So go back to the rolling of a six-sided die. Now, if you're interested in seeing an even number rolled, then the following is how we would correspond to those terms we just outlined. So S, the sample space, that would be 1, 2, 3, 4, 5, 6, all the possibilities. Each number, 1 through 6, those are possible outcomes. And then seeing an even number, that would be an event. So the event A maybe would be 2, 4, 6. So notice that here we have an event, but it's satisfied by multiple outcomes. So sometimes we may be interested in complement events. So a complement event, which we usually define as not A, is basically just everything that's not in the event you're interested in. So on the rolling the one six-sided die, if we define A to be the die lands an even number, then our event A happens whenever we roll a 2, a 4, or a 6. So then the complement, that would be not A, which would be the event that the die is not an even, in other words, an odd, and that would include the numbers 1, 3, and 5. So notice that between the event A and the complement, not A, it makes up our entire sample space, and that will always be true. Sorry. We may also be interested in looking at when two events occur at the same time. So pictorially we can represent this with Venn diagram. So if I have an event A and event B, the intersection A and B, that's going to be wherever those two things occur at the same time. So go back to rolling that six-sided die. If A is the event that the die lands on an even number, so a 2, a 4, or a 6, and maybe we define B as the event that the die lands on a number greater than 3, so that means 4, 5, and 6 would all work. Then the intersection, A and B, these are going to be the outcomes where the die is even and greater than 3, so that's going to be where these two sets overlap. That's going to happen when you either roll a 4 or a 6, because a 4 and a 6 occur in both A and B. We may also be interested in the union of events, so that means when either one or the other occurs. So go back to the six-sided die, where we define A as an even number and B as a number greater than 3. So if I'm looking at the union A or B, that means it only has to be even, or it could be greater than 3. So 4, 5, and 6 make it, and then also we need to include 2. Oh, I have a typo here. A 2 should be included in here because a 2 is even, so I need to fix that on my slides. A 2 should definitely be a part of this right here. Okay? So if it's in one or it's in the other, it gets included. Now, it's possible that two events might not ever happen at the same time. So if this is the case, then we say those events are mutually exclusive. So in this Venn diagram, you can see A's over here, B's over here, no overlap. So looking at an example here, let's say that A is the event O lands on an even number, B is the event that the die lands on a number divisible by 5. Well, 5 is the only one divisible by 5. 2, 4, and 6 are then even numbers, and so in this case A and B can't happen at the same time, so they're said to be mutually exclusive. In other words, if two events A and B are mutually exclusive, what we're basically saying is that their intersection, the probability of actually seeing an intersection is 0. Okay, so they don't overlap. So that's mutually exclusive. Now, the fact that they're mutually exclusive and they don't overlap, that makes it really nice for calculating probabilities associated with mutually exclusive events. So if I have two events A and B and I want to calculate the probability of A or B. Well, since there's no overlap here, I can just take all this probability of A and add in all this probability of B, and that'll get me my probability of one or the other. So here's an example. So at CBC, a full-time load, that's anywhere between 12 and 18 credits. So if I know that 14% of students are less than full-time and 8% of students are overloaded, right, so that means over 18, what's the probability that a randomly selected CBC student is rolled at a level other than full-time? So you have this event A, less than full-time, B is overloaded. These two events are mutually exclusive because a student can't be both less than full-time and overloaded. So then if I want to calculate the probability of A or B, I can just add the two probabilities separately. So the probability of A or B, that's going to be the probability of A plus the probability of B because they're mutually exclusive. So it's going to be 0.14 plus 0.8. That's going to be a 22% chance of seeing that happen. And again, I can only add these together like this because those are mutually exclusive events. So let's go back to the six-sided die. Let's say that we define the event A to be that the die lands on a multiple of 3. What's the probability of A and what's the probability of its complement? Well, A is going to happen only when we see a 3 or a 6. Not A is going to be everything else, 1, 2, 4, and 5. So the probability of A, well, that's 2 out of 6. That's a 1 in 3 chance. And the probability of not A, that's 4 out of 6. That's a 2 out of 3 chance. And these would be the decimal representations. And what you'll notice is that when you take the probability of A plus the probability of its complement, they add up to 1. And in fact, this is always true. So this complementation rule gives us a nice way to calculate probabilities if we know something about the complement. The probability of an event is always equal to 1 minus the probability of its complement. This is useful because sometimes we're going to find out it might be easier to calculate a complement probability than the initial probability itself. So let's look at an event here. So in this example, the table shows the sizes of different farms in America. All right. So we've broken down to a bunch of different sizes in acres and given each event a letter. Now, if I wanted to know what's the probability that a farm is less than 2,000 acres, well, I have a lot of categories that are less than 2,000 acres. In fact, events A through H are all less than 2,000 acres. So if I wanted to calculate the probability of being less than 2,000, I could feasibly just add all these numbers up, right? But we could also recognize that a farm being less than 2,000 acres is just the event, not I, right? So look back. Here's I, 2,000 and over. Everything else is just not 2,000 and over. So if I want to calculate the probability of not I should just be able to do 1 minus the probability of I. Well, 1 minus the probability of I is 0.035, and 1 minus that is 0.965. So in this case, we can see that it's easier to just take the complement and subtract it from 1 rather than going through and having to add up a whole bunch of numbers. This just makes it a little bit quicker. We just have to do one calculation instead of a whole bunch of additions. So now, things get a little trickier though when we don't have mutually exclusive events. So consider two events that are not mutually exclusive, meaning they have some amount of overlap. Now notice when they overlap, if we just add up A and B, what we've done is we've actually counted this intersection twice, right? I added all up from A, added all up from B, and then boom, everybody in here got picked twice. They got counted twice. So how do we correct that? Well, it's actually pretty simple. If I know my intersection is in there twice, I'm just going to take it out once. So what that gives us is this general rule for addition. So if you have any two events A and B, the probability of A or B is always going to be the probability of A plus the probability of B, and then subtract off the intersection right here. So this is a general rule, and this applies for any events, not necessarily mutually exclusive events. So it's nice, it's more general. Let's look at an example. So arrests in the U.S. show that 76.2% are males, 15.3% are minors, and 10.8% are males and under 18. So what I want to know is what percent of males are either, or what percent of arrests are either male or under 18. So I like to define my events with letters. So let's say A is the arrested person's male, B is the arrested person is under 18. And if I'm trying to calculate the probability of A or B, I know I can take the probability of A plus the probability of B and then subtract off their probability of their intersection. So the probability of A, male, that's 0.762. The probability of B, which is minors, that's 0.153, and then the intersection is 0.108. So together, all that should come out to 0.807. Right. Now, the data from arrest, we could also use what's known as a contingency table to try to solve this problem. And in a contingency table, what we do is we look at two events and we put them into like a little 4x4 table. So in this column are all the males, in this column are all the non-males. Here's all the underage arrests, and here's all the not underage. So down here at the bottom of the males, we can see that males have a 76.2% chance overall. To be underage is 15.3%, and to be male and underage, see where they intersect, is 10.8%. And now, since we know that these two boxes have to add up to that, these two boxes add up to that, everything has to add up to 1, then we can actually fill in the gaps by calculating difference. So if I take this minus that, it should give me here. Okay. So then we can complete the data and look like this, and we can actually look at the probability of male or under 18, and it adds up. See, so males are here, under 18 is there. If you add up these three spaces, then you'll be able to see that they should add up to 0.807 like we got last time. Typically, when we're using a contingency table, these values on the inside, these are called joint probabilities because they're the intersection of two events. Like here's males and underage, so they happen jointly. And then on the outside, these are marginal probabilities. So this is just males in general. This is just underage in general. It's not necessarily worried about what's going on with the other event. All right. Okay, so let's think of a different scenario here. Let's imagine we're playing a game and we're rolling 2 dice, and I offer you the opportunity to bet on an event. The event I'm going to offer you is that A is that the sum of the 2 dice is 8. So if you win, you'll receive 5 points extra credit, and if you lose, I get to delete your highest quiz score. So what I want to know is what's your probability of winning. So without any other information, we're just going to have to consider probability of rolling an 8 overall. So here's what you need to do. You need to go take a look at a table of all the possible outcomes for rolling 2 dice. There's one in your book. Okay, so you want to take a look at that table. And you'll notice that there's 36 ways to roll 2 dice. So 6 options on one dice, 6 options on the other. So together, that's 36 options. And if you count up all the ways that you can roll an 8, there's going to be 5 of them. Okay, so there's going to be like a 2, a 6. You can get 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. Okay, 5 options. So the overall probability of rolling an 8 is just going to be 5 out of 36. That would be 0.139. Okay. Now, what if, though, I gave you a hint or I gave you some information? I said, okay, I rolled the 2 dice. The sum of the dice is even. Now, would you want to bet? So see, what's happened here is I've told you that the dice land on an even score, so I can eliminate all the odd possibilities. So there's 36 ways to roll 2 dice, but I've just eliminated 18 of them. So now there's only 18 possible ways that the rolls could have ended up because there's only 18 even rolls. And so then the updated probability is going to be the probability that of A given that the sum is even. So there's still 5 ways to roll an 8. There's only 18 ways to roll an even. So now look, our chance of rolling an even number has gone up based on the information I gave you. Because the probability of an event changed based on information I gave you, we would say that these two things, even numbers and 8s, are dependent on each other. Okay, this is an example of a conditional probability. The notation that we use for conditional probability of A given B. So if I want to say the probability that A occurs given that B has occurred, we use this horizontal line. So this is the probability of A given B. And actually, we can derive the general formula by looking at a Venn diagram. Okay, so you have some general sample space, and say A's here and B's here, and there's some overlap. Okay, well, if I know that B must occur, right, so I'm given B, that means I can toss out all of this stuff in our sample space that I don't care about, right? And all I'm left with is just B. Well, if I have to be in B, well, where's the only place that A can occur? The only place it can occur is at the intersection, here in A and B. So it would make sense then that if I'm trying to calculate the probability of A given B, that means I have to be in the intersection. So then the general formula is that the probability of A given B is the probability of the intersection divided by the probability of the given condition. So let's look at the example with the arrest in the US. What if I wanted to know what's the probability that an arrested person is underage given that they're male? Well, if I wanted the probability of underage given male, I should just be able to take the probability of underage and male, divide by the probability of male because that's the given condition. That's going to be 0.108 divided by 0.762, which will give us 0.142. The general formula can also be reordered. So here's the general formula, the probability A given B equals probability of A and B over probability B. Now if I multiply both sides by the probability of B, then I'm going to get that the probability A given B times the probability of B is equal to the probability of A and B. And this is maybe sometimes referred to as a general multiplication rule. And it can help us solve certain types of problems. So let's look at an example. So a poll showed that in the upcoming Super Bowl, 59% of students plan to watch, and for CBC students who do plan to watch, 32% of them will be polling for the Denver Broncos. So what's the probability that a randomly selected student will watch the Super Bowl and be rooting for the Denver Broncos? So let's say we define W to be that the student's going to watch, B to be the student that's going to be polling for the Broncos. What I'm really looking for here is what's the probability that they're watching and polling for the Broncos? Well, based on my formula, I know that I should be able to calculate that by taking the probability of B given W times probability of W. The probability of rooting for the Broncos given that they watch, that's 32%, right? That comes from our problem. The probability that they're going to watch overall is 59%, and that comes out to 0.189. Now, you're welcome to memorize this formula if you'd like. I typically don't. I typically actually solve these using a tree diagram. And so in a tree diagram, we just split each outcome and start looking at all the possible combinations. So first, I'm going to split between watching people who watch the Super Bowl and people who don't. And then of those who watch the Super Bowl, they either pull for Denver or they don't, or those who aren't going to watch it, they pull for Denver or they don't, or I don't know because they're not even watching. I really don't actually care about these people because remember, I'm just trying to figure out the probability of watching and pulling for Denver. So you'll notice on this branch, what's the probability of watching the Super Bowl? Well, that's 59%, which means 41% must not be watching it. And then of those who watch the Super Bowl, apparently 32% are pulling for Denver, which means 68% must not be pulling for Denver. And you'll notice that we could actually get the correct probability by figuring out, okay, well, what branch do we want to land on? We want to land on the branch where people watch the Super Bowl and pull for Denver. And with the probabilities on the branches, I can see that all I have to do is multiply across the branches to get that 0.59 times 0.32, and that's exactly the calculation we did on the last slide. Okay, so tree diagrams can really simplify these problems. If you don't want to memorize more formulas, I use tree diagrams. Now, let's consider drawing a card from a deck of 52. And let's say that the event A is that the card's a king, the event B is maybe that the card is a diamond. And I want to look at what's the probability of A, probability of B, and then I want to look at the conditional probability. Alright, so if we're just looking at the probability of a king, well, there's 4 kings out of 52, which reduces to 1 in 13. So there's a 1 in 13 chance that you get a king. If you look at the probability of B, so the card's a diamond, well, 13 diamonds out of 52, that reduces to 1/4. Now, if we calculate the probability of A given B, okay, well first, what's the probability of A and B? That's the king, it's a king and a diamond. So how many king of diamonds are there? Well, there's 1 king of diamond out of 52. What's the probability of B? Well, we already got that, that's 1/4. Well, 1 over 52 divided by 1/4, dividing by 1/4 is the same as multiplying by 4 over 1, so that gives us 452, which is 1 over 13. And now notice, my conditional probability of A given B didn't change. It's exactly the same as my probability of A. This actually tells me that knowing B doesn't affect the probability of A. In other words, I told you the card was a diamond, but that doesn't change your probability of getting a king, right? I might as well not have told you anything because I didn't help you out. These two events are an example of what we call independent events. The general definition of independence says that all you have to do is check, is the conditional probability of A given B equal to probability of A, or similarly, is the probability of B given A equal to the probability of B? So if you're trying to check if two events are independent, calculate their probability, calculate their conditional probability, and see if it changes. And if it doesn't change, then it tells you they're independent. Now, notice, if two events are independent, then that means the probability of A given B equals probability of A. Well, if we take the definition, the formula for calculating the probability of A given B, which is the probability of A and B over the probability of B, and we multiply that probability of B over to the other side, what we can actually get is a special multiplication rule for independent events. It turns out that if you have independent events, say A, B, C, D, say they're all independent, and you want to calculate the probability of A and B and C and D, all those occurring, you can just take the probability of A times the probability of B times the probability of C times the probability of D, and so on. Okay. Now, this only works for independent events. If they're not independent, then we need to fall back on our general formula or a tree diagram. Okay, but if they are independent, then we can actually just multiply their probabilities together. So, pretty cool. So let's look at an example. Let's say that you're going to roll a six-sided die, and you're going to do it 3 times, and you want to see an even number followed by a multiple of 3 followed by a number less than 3. Now these events are all independent because each roll is completely unaffected by the roll before it, right? So if I roll an even number first, it doesn't affect my probability of rolling any number on my second try. The dice doesn't know, it's not alive, okay? It's an equal chance every time. So if I want to take the probability of even and a multiple of 3 and less than 3, since these are independent events, I can just take the probability of even times the probability of multiple of 3 times the probability of less than 3. And so evens, there's 3 out of 6. Multiples of 3, there's 2 out of 6. Less than 3, there's 2 out of 6. Multiply them all together, you'll end up with 118. Okay? Now, in the basic definition of probability, we had to figure out, how many ways can an event happen. Now this can get complicated pretty quickly depending on the scenario, so we want to talk about some counting techniques. And to introduce this idea of counting, I want to start maybe with our license plates. So in Washington, a standard license plate has 3 letters, 4 numbers, and I might want to know, hey, how many unique plates can we make? So to solve a problem like this, I like to break it down into slots. So here's like the 7 slots that are open on a license plate. So in the first slot I can put a letter, here I can put a letter, here I can put a third letter, then I can put a number, another number, another number, another number. And I like to think about, okay, how many ways could I pick things to go in that slot? Well, for letters, there's 26 letters to pick from. 26 letters to pick from here, 26 letters to pick from here. Here there's 10 digits I can pick from, 10 digits here, 10 digits here, 10 digits there. And it turns out that if I want to calculate the total number of plates, we can actually just multiply all the number of possibilities. So it gets pretty big. So the number of plates is going to be 26 times 26 times 26 times 10 times 10 times 10 times 10, which comes out over 175 million. Okay, so there are lots of possible unique license plates that we can make under this this sort of scheme that we have in Washington. So multiplying like this is always a possibility, and this is based on actually what we call our basic rule of counting. So if you have 2 events or more, one of which can happen n ways, the other can happen m ways, all you have to do is multiply the number of ways together to figure out how many ways they could happen at once. All right. Now it gets a little more complicated as things start to change. So in the license plate example, we say that those numbers and letters are picked with replacement. And we say that because numbers can repeat. So imagine you have all 26 letters in a big pot, and you pull out an A and you put it on your license plate. Well, with license plates, I get to throw that A back in the pot, and I could pick it again next time. It makes sense that the numbers can repeat or they can be replaced. But sometimes replacement isn't really a possibility. So Suppose I have a box of 5 textbooks, and I have room enough on my bookshelf for all 5 of them. So how many ways can I arrange the 5 books? Well, I'm again going to break it into the 5 slots that I have on my bookshelf. So in the first slot, there's 5 ways I can pick that book because I have 5 books. Now, when I get to the second slot though, I can't replace that first book back into the box. So now I only have 4 books to pick from. Once I place that one, I only have 3 books, then I only have 2 books, then I only have 1 book. So then the solution here you can see is 5 times 4 times 3 times 2 times 1. That's 120 unique arrangements. In counting, we see this pattern where we're multiplying by decreasing numbers. We actually give it a notation. So this is what we call a factorial. So in factorial, we use the exclamation point. It's basically that number multiplied by every number below it all the way down to 1. So as an example, if I wanted to calculate 7 factorial, then 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. You can write it down. You can try it out. It would be 5040. Now, it gets even a little more complicated though when you might not be necessarily rearranging all the items. So let's say I have those 5 spaces on my bookshelf, but I have 10 books to choose from. And I want to know how many ways I can arrange those 10 books into 5 spaces. So again, I can break it into my 5 slots. Okay. Now in my first slot, I have 10 books I could put there. Then I place one, I have 9, then 8, then 7, and then 6 left. Okay. So solution here is 10 times 9 times 8 times 7 times 6. That's 30,240. That's using the basic rule of counting. But what I really don't want to have to write out a bunch of slots and do this every time. So we want to come up with a shortcut. And the way we can do this, let's take this product 10 times 9 times 8 times 7 times 6, and I want to rewrite it. So on the top, I'm going to add in, so 10 times 9 times 8 times 7 times 6, that's what we started with. Now I'm going to multiply by 5 times 4 times 3 times 2 times 1 on top. But then I'm going to immediately divide out 5 times 4 times 3 times 2 times 1. Essentially, I'm just multiplying something in and dividing it out. And what am I multiplying in? I'm multiplying in a 5 factorial. So on top now, we have 10 factorial. On the bottom, we have 5 factorial. And so then what I can rewrite that as 10 factorial over 10 minus 5 factorial. And you'll notice that 10 was the number of books we could pick from, and 5 was the number of books that we had room for. So this gives us our general pattern for permutations. So in general, if you want to figure out the number of ways that R items out of a total of n can be arranged, we calculate that as the permutations of n items out of R. You can calculate that by doing n factorial over n minus R factorial. So permutations is just another fancy word we use to say rearrangements or arrangements. Most calculators have both a factorial button and a permutation button. So if you can't find it, you should ask. But if you don't have one, you might want to consider getting a calculator with those permutation functions on there. So let's look at an example. So suppose you have a raffle with 3 top prizes. So the first place is, these are all gift cards to a local restaurant. The first place is $50, second place is $25, third place is $10. And if 42 people buy tickets, how many different ways can winners be selected? So in this case, what we're really asking is, how many ways can you rearrange 3 winners out of 42 total? So using my formula, NPR, so N is 42, that's total. R is 3, that's how many I'm picking. I'm going to take 42 factorial, divide by 42 minus 3 factorial, and that's going to end up giving me 42 factorial over 39 factorial. You can either simplify that or plug it into your calculator, but either way, you're going to come out with 68,880 unique winning combinations. Now, suppose though we don't want to treat our rearrangements as unique. So in this example, imagine that I want to take a sample of 4 students from a class that has 25 in it and give them a survey. They're going to give me feedback. Now, how many unique samples could be made? Now, let's suppose I take a sample and I end up with maybe Alexis, Jacob, Mallory, and Tim. Okay, so that's, say, A, J, M, T. Now, does it really matter what order I pick them in? And I would say it doesn't, because at the end of the day, whether Jacob came first or Tim came first or Mallory came last. It doesn't matter because I've still got a survey from those 4 people. Okay, it's not like getting picked first is going to change the way you answer the questions. Okay, so basically, you know, if I get Alexis, Jacob, Mallory, Tim, Alexis, Jacob, Tim, Mallory, ATJM, ATMJ, AMJT, dot, 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 all of these events, they're separate arrangements, they're separate permutations because they're reordered, but for me, I don't care. I treat all of these as the exact same sample because I have the same 4 people. I want to group them all into what we call one combination of a sample. So in general, we can calculate combinations. It's a similar formula to the permutation. So the n factorial over n minus r factorial, that's the same as permutation. But what we're doing is we're going to divide out an extra r factorial because this r factorial is the number of ways that the samples can be rearranged after you pick them. Okay, so it's going to be a little bit smaller. There's not going to be quite as many combinations as there are permutations. So how do you know whether you should be calculating combination or permutation? So I always ask myself, does order matter, basically? If the order matters and rearrangements are unique, then it's a permutation. If the order doesn't matter and you want to treat everybody, all the rearrangements as one combination, that's where you're looking at combinations. Okay, so if we revisit the sampling example, right, I want 4 students from a class of 25, then the unique samples, well, since being the order you're picked in doesn't matter, I'm going to use a combination, so that's going to be NCR, which is n factorial over r factorial times n minus r factorial. N is 25, r is 4, so that reduces to 25 factorial over 4 factorial times 21 factorial. You should be able to simplify that to 12,650. Again, you should have a combination button on your calculator as well. So factorial, permutation, and combination, those are all on your calculators. And again, if you are having trouble finding it, you can either ask me. You could also probably just, I think, Google it or YouTube it. Just say combinations on blah, 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 and put in the title of your calculator. All right, so that's it for probability and counting. Hopefully that's a good enough review to get you started for your homework. And I'll see you next time for Chapter 5.